Welcome and thanks for coming. I'm happy to talk about performance tuning for Apache Pulsar Kubernetes deployments in the cloud. I'm Lari Hotari, Apache Pulsar committer and PMC member. I've worked on the Java platform since 1997 and contributed to open source for over 20 years. I love open source. At DataStax, our mission statement is to serve real-time applications with an open data stack that just works. Therefore, in my team, customer reliability engineering, we focus a lot on improving Apache Pulsar's resilience and reliability. In my original abstract, I mentioned that I would demonstrate how to detect and fix a bottleneck. I have changed the structure since I think that being successful with performance engineering requires a systematic approach. I want to take you on a journey with me to learn about performance tuning for Apache Pulsar Kubernetes deployments in the cloud. This won't give you a cookbook recipe to make Apache Pulsar go fast. Instead, I hope this will give you tools to organize your performance tuning in a way that you can achieve the goals that you have. So we'll go over performance tuning in general, Apache Pulsar Kubernetes deployments, scaling out and scaling up, and having an overview of tunable configurations. You get into performance tuning when something is dead slow. And you think of going fast being the solution. What about short time to recover? And how about efficiency? What is the goal of the performance tuning? It's fulfilling the quality requirements and constraints of your system. And it's improving the price-performance ratio to reduce cost. There are multiple performance aspects. One of them is latency of operations. There, the measurements are usually done in percentiles such as P50, P75, P90, P95, P99, P99.9, and also there could be a metric of maximum latency. The mean and average could miss a lot from the user experience perspective. However, it could be a useful metric for efficiency. The throughput of operations is about the rate of operations that the system is handling. And this is related to the capacity requirements that your system has. There are multiple different aspects of this quality of operations. For example, efficiency, usability, responsiveness, correctness, consistency, integrity, reliability, availability, resilience, robustness, recoverability, security, safety, maintainability. In general, there could be metrics around errors on the systems that is the way this is measured. In this quality, it impacts the value and cost of the system. So what is performance tuning? Here's a way to think about it and to do performance tuning. Many times in any improvement process, there's kind of like this cycle of first observing and learning, then deciding on some actions and then acting. And similarly, in here we have something where we first learn and assess our system that we're tuning. Then we do measurements, we identify bottlenecks, and with the goal of eliminating the bottlenecks, we do some modifications and tuning. And as a validation, we measure and validate that we are getting the expected results from this modifications and tuning so that the bottleneck is eliminated. And then we go on another cycle of finding the next possible bottleneck and eliminating that. There's also another systematic approach, which is for identifying these bottlenecks. So this use method introduced by Brendan Gregg, and here's also this diagram from Brendan Gregg's webpage about this use method. So it's simply as defined as for every resource, check utilization, saturation, and errors. And this is intended to be used early in a performance investigation so that you could detect these systemic bottlenecks. So it's kind of like related to this cycle, but at another level. So these methods together could be applied. For systems in production, Site reliability engineering defines these 4 golden signals for monitoring, and these are latency, traffic, errors, and saturation. And the SRE book recommends that if you measure some metrics in your system, it should be in these categories that you're focusing on. This is kind of like related to the previous use method, but this is more like focused on production system and monitoring the metrics in production. And obviously, like this use method could also be used in production, but kind of like that aspect is a little bit different. So latency is the time that takes to service a request. Traffic is how much demand is being placed on your system, and typically this is measured in a messaging system. It will be messages per second or bytes per second, which are also some metrics that there are in Pulsar. Errors are the rate of requests that fail either explicitly or implicitly, that your system isn't able to serve the request, or then it returns with an invalid response. Saturation is a measurement of how full your system is, typically defined as also as amount of requests that are waiting to be served. So then going into the Apache Pulsar deployment options, there are multiple different open source Helm charts for deploying Apache Pulsar. So the one in the Apache Pulsar project, DataStax has a Apache Pulsar Helm chart, and Stream Native has a Apache Pulsar Helm chart. Then various vendors have some operators which might not be fully open source. Here we're taking a look at the Helm chart options. So going into the observability options for Pulsar Kubernetes deployments, the Helm chart can deploy Prometheus and Grafana, and also some dashboards for monitoring Pulsar components. So the Pulsar broker, bookkeeper, and zookeeper nodes. In this presentation, I'm not going into details of these dashboards, but just displaying at a high level, like what they look like. So this is a screenshot of a broker metrics dashboard. There are multiple dashboards for the broker, and this is only one example of this. Then there are for bookies, there are dashboards, and also for Zookeeper. The Pulsar architecture for Kubernetes deployments is such that there is a separation of a serving layer and a storage layer. And for the serving layer, the Kubernetes deployment comes with Pulsar proxies in front of the Pulsar brokers. And in Pulsar, the storage layer is handled with bookkeeper bookies, and there's also cloud storage is used for tiered storage. And the system metadata and coordination is handled with Zookeeper. Performance model is something that could help in understanding performance tuning. I found this definition in encyclopedia.com, that a performance model is a model created to define the significant aspects of the way in which a proposed or actual system operates in terms of resources consumed, contention for resources, and delays introduced by processing or physical limitations. The creation of a model can provide insight into how a proposed or actual system will or does work. And a similar idea was brought up by Jack Van Lightly in a blog post, The Importance of Mental Models for Incident Response. And here in this blog post, he says, it starts with your mental model of the system. The more complete and more accurate the model, the faster you are likely to be able to diagnose and remediate the issue. It's both a map, but also an understanding of how components interact that allows you to infer how signals in one part of the system can explain behavior seen in another. In Jack's blog post, he had this aspect of using these mental models for incident response, but likewise, these are important for performance tuning and in understanding like what are the bottlenecks in your system which you trying to eliminate. So here I'm introducing some models that could help us understand like what is going on in the Pulsar broker when a message is sent to Pulsar. So I have a diagram about the write path and also the read path, which is about consuming. And these are a simplification of what is going on. So it doesn't mean that this is actually the truly implemented in this way. So there's a saying that all models are wrong and some are useful. And this doesn't describe the accurate sequence of actions. But the purpose is to get a high-level understanding of the right path and what. So getting a mental model and being able to understand that in a better way. And this will also help in interpreting like the different dashboards that you have in Grafana, that you know what to look for when identifying a bottleneck. So we won't have time in this presentation to go in detail like how this could be connected, but that could be a possible subject of another talk where we would go into more details. So on the right path, there's everything starts in the Pulsar client, and the Pulsar client has a producer that puts these messages first into a batch message container. So Pulsar does batching by default, and it uses a Netty framework in its network operations, and in that part I've mentioned here because in tuning there could be some parameters that are related to Netty client and Netty server, and especially if making changes to Pulsar, those could be there could be more relevance in understanding the Netty level details of the implementation. So there's a Pulsar binary protocol that is used between the Netty client and Netty server parts of between the client and the broker. And from the server side, they get it moved on to a producer. Then there's a representation of a topic in the broker, and then a managed ledger. When the messages are written, they are added to an entry cache, which is also called a broker cache. And this is something that we'll look in later when we get to the consuming part, like how this entry cache behaves. When using a replication factor of 2, in case of Bookkeeper, it's called write quorum. That's there will be 2 calls to storing to Bookkeeper. So this part to from the Bookkeeper client to the bookie, this will be executed at least twice for each message that is written. And on the bookie side, there's a write cache, and then the entries. I didn't mention that earlier, but they're not anymore messages that are written to the bookies, but it's called an entry because the entry could be a batch message which contains multiple messages. So this happens this way, that it's written to the journal and asynchronously from the journal to the actual storage. So when the call will complete from the broker's perspective, once it has f-synced the write to the journal. And as we can see from this diagram, these are the parts where disk operations are involved, and that is a area which typically becomes the bottleneck, the disk IO. And one optimization opportunity could be to be able to minimize disk IO or optimize that. And there are multiple settings to do that, but we won't be going into those details. But when using this approach as a guideline for doing optimizations, you'll be able to find your way into what area you should be looking at and where the opportunities for optimizations lie. Then on the read path, the Pulsar client has a consumer, and in that use again Netty to talk to the server side. And there are multiple different concepts and in instances on the server side related to consuming. So there's a consumer and a subscription, which are kind of like related in the implementation. There's a topic, there's a dispatcher, there's a managed cursor. Then again, the same managed ledger and entry cache and bookkeeper client. So the reading happens in a way where it would first look up entries in the entry cache and the broker cache. So if it finds the entries to read there, it doesn't have to do the slow path all the way to bookkeeper. And that's one place where there's a significant optimization, where if it doesn't have to do this slow path. And optimizing the usage of the entry cache is one of the important things to do when tuning Apache Pulsar. One thing to keep in mind is that the read path isn't really a complete read-only path, but all the message acknowledgements will be writes. So there's also writes that are involved when messages are being consumed. So that will behave a bit like the write path when these acknowledgements are handled in the case of the consuming, and that's not displayed in this diagram. So if there's a entry cache miss for reading the entries, then it'll have to go to the bookkeeper all the way over the network. And on the bookkeeper side, the entries are first looked up in a write cache, and that's, as we saw in the previous diagram, when writing the entries, they were put into a write cache. So that's how on the bookie side, it could be prevented that we don't have to go all the way to the disk to read the entries, and it could return back if it finds it in the write cache. Then the next step is to go to the read cache, and this read cache is a read ahead cache, which could also contain the entry. So when we go to the disk, we don't just read one message from the disk, but instead we read ahead, and that is I think the default might have been like 1,000 entries that it reads ahead, or even more. So that's what happens when entry is read, that instead of reading just one, when there's a cache miss, it'll read the read ahead amount of entries. So that is one additional way how it is there's an optimization to prevent going to disk. But for this optimization to be effective, this requires sticky reads, and that's something that is enabled by default in Pulsar. But that requires settings that the ensemble size and the write quorum size are equal, and this isn't documented in Apache Pulsar, or it wasn't documented before. I've recently submitted a pull request to add documentation of that. So if there's not sticky reads, the reads for subsequent entries are spread out across the bookkeeper nodes, which contain the entries. So it's, if there's a replication factor of 2, it would send the first request to the first bookie, and then for the next entry to the next bookie. And this would cause both of the bookies to have their read ahead caches contain the same entries. So with sticky reads, the same ledger would be using the same bookie if it's possible. And then there's a better efficiency of the read ahead cache. And here as in a similar way as we were discussing, the main optimization is around preventing going to the slow disk, which is always a relative concept. So there are several messaging workload edge cases to cover when testing and performance tuning a Pulsar cluster. And these are something that are important to test for. One of them is a so-called catch-up read, which is also called a cold read. And this is a case when the entries aren't found in the entry cache for certain reasons. Let's say you have a large amount of consumers that are starting up later than the producers, and in that case, the entries aren't no more in the entry cache, and when they connect, all the consumers will have to go the slow path to the disk. And that is why it causes a lot more load on the system, in making sure that the setup can cope with the load in these scenarios is important. In the kind of like the opposite of a catch-up read is this tailing read, when producers and the consumers are all online. In those cases, it should be made sure that the cache is efficiently used and sized, so that in a hot read scenario that no cache misses happen, so that there isn't additional unnecessary load on the bookies. Then there's also like other types of scenarios that you have extremely high amount of consumers and subscriptions, and in those cases could be very special for these catch-up and tailing read scenarios, in having the full combination of what the configured system can handle. They're like finding those limits is important in tuning the different cache sizes and parameters accordingly. So this presentation doesn't go into the details of doing that, but it kind of like gives you starting points of doing that. And there are also like cases where you have fast producers and consumers that a backlog is gathering up. In those cases, at some point, it will fall so far behind that with the configuration parameters that Pulsar contains, by default, it considers consumer being too far away that it doesn't do any caching. It's I think it's 1,000 entries by default. So then in that case, it wouldn't be using the broker cache, and there could be the possibility to tune that so that it keeps the broker cache, like more entries in the broker cache. But they're like, depending on the case, it could be very different. So then a high level of what could be modified and tuned in Apache Pulsar Kubernetes deployments. So there's the possibility of scaling out Kubernetes deployment horizontally, then scaling up vertically. And in those, there's different Kubernetes resource requests and possible limits, and tuning the JVM settings for components to take use of the resources. Then there's a possibility of changing cloud VM types. Then, as mentioned, there's Apache broker configuration, as we were talking about the broker cache a lot. That's one area. There's Pulsar load balancer settings, which impact the decisions how Pulsar is balancing the load across brokers. There's also bookkeeper client configuration, and then which is in the broker side, and then bookkeeper configuration on the server side. So horizontal scaling is about adding more of these copies of these components, which are deployed as like each node is a pod in Kubernetes, and having more of these. And vertical scaling is increasing the resources for each individual pod. And there's also like the vertical scaling could happen also at the Kubernetes node level, that having bigger nodes and different types of nodes to run the pods. So for brokers, zookeepers, and bookies, Kubernetes stateful sets are used. It is very easy to increase the size of a stateful set in Kubernetes. Increasing can be done without taking down the cluster. This could be done for brokers and bookies. But then scaling in, so reducing the cluster size, this is a manual operation for bookies, and this should be done with care. And there's currently no automatic solution for this in open source Pulsar Kubernetes Helm charts. So there's a operation called bookie node decommissioning, which should be done before or at the removal of a bookie. And this Zookeeper cluster size modifications, these should be done with more design and care, since Zookeeper doesn't scale linearly. It's typically better to stick to a size of 3 or 5 nodes. For proxies, there's a replica set, and the size could be easily increased and decreased online. So the vertical scaling options in Kubernetes, the scheduler will take care of running the workload on the nodes with the requested CPU resources and memory amounts. So this could be easily changed, like the request memory size and CPU size. And the disk volume sizes, types, and amounts could be also adjusted. One detail is that in a stateful set, all the pods will get the same amount of resources. In some cases, there might be a need to, because of cost reasons, to run, let's say, a single bookie on a single Kubernetes node in a VM. And this could be done in also. So that's one option for vertical scaling. Mainly mentioning this in this presentation, not really explaining in detail like how that could be achieved. But this could be needed when certain network or disk I/O throughput is required for a very high performing bookie node. So the Java JVM options tuning, there's the heap size and direct memory size that are the main parameters. And this applies to broker, proxy, and bookie, and Zookeeper. For the Zookeeper, currently the direct memory size doesn't have a huge need. So the defaults are mentioned here, and one note about the tuning is that the defaults aren't that great, and there could be a need to tune things. That, for example, if your broker runs out of memory, it's better that it exits the process instead of like continuing in a possible broken state, because in Kubernetes it'll automatically replace the node with a new one if the process crashes. So that's a better option than leaving inconsistent state behind. One detail is that Java processes consume more memory than the max heap size and max direct memory. So that's a common mistake, to set the resource limits to the sum of the maximum heap size and maximum direct memory size. You should be allocating at least 20 to 25% more RAM than the maximum heap size and direct memory size. And it's better to just use resource requests and not use limits at all, since there's the risk of getting the process killed when it goes over the limit. So a quick note about the vertical scaling of cloud VMs. So there's multiple types of cloud VMs that can be set for a Kubernetes node. You have to kind of like a Kubernetes node doesn't directly map to a single pod, but there's the scheduler will run many pods on that by default. But this could be changed, that if you want to do a configuration where you just run a single bookie on a single Kubernetes node, this could be achieved with Kubernetes taints and tolerations and separate Kubernetes node pools. So for cloud storage options, these have a great impact on the performance of Bookkeeper and Zookeeper. And first of all, SSD disk type is needed. So Bookkeeper and Zookeeper are not optimized for spinning disks. And for cloud disks, they're typically fairly high throughput, but not so high IOPS. And this works fairly well with Bookkeeper, and there are parameters for tuning this. So IOPS means IO operations per second. In Bookkeeper, it groups the fsync operations with this parameter called journal max group weight msec parameter. And kind of like a rough calculation from that is that it would go to about 1,000 IOPS per second for writes when using a setting of 1. But then if you change that to 2, there will be a slight increase in latency, but that would reduce the number of maximum number of IOPS for writes to about 500 per second. So this could be a useful setting to tune. One detail is that increasing the size of the journal disk is important optimization in many cases, because larger cloud disks come with more IOPS and more throughput. And you might want to put for example, the journal disk size to a much larger size than you would actually need from the size perspective. For example, you might only need a 10 gigabytes for the size, but then you might be setting it to 256 gigabytes just to get a lot more IOPS. And for example, for GCP, you could check online from this webpage, like the different impacts of the different size parameters. There's also like other Bookkeeper storage options, and like, for example, running a without journal. That could be an optimization in the cloud. I'm not going into that in detail here. There's the replication factor, which defaults to 2 in Pulsar. It's typically a good default to use 2 in the cloud, since the cloud storage is already redundant. It's good to remember that sticky reads aren't used unless E equals QW, so this write quorum. And using a striping setup will have a negative impact on reads. There's also the possibility of having multiple journal disks and multiple ledger disks. And there could be a configuration around rack awareness and availability zone awareness when a setup needs to tolerate total availability zone outages. So for the Pulsar broker configuration, it's important to do the broker cache tuning so that catch-up reads can be handled efficiently. And there are quite a few improvements which aren't yet in released versions of Pulsar. So this is an evolving area where there's improvements are being delivered in upcoming Pulsar versions. There's also Bookkeeper client tuning for back pressure handling. That's also an evolving topic. And that could help in certain cases where there's heavy write or read load, that the broker doesn't run into a situation where it's overloaded in a way that the memory runs out. There's also like some small details that Pulsar load balancer tuning, like in cloud environments, it might not detect properly the network interface speed, which is needed for load balancer resource calculations, and that has to be explicitly configured, at least in AWS. So the key takeaways are follow a systematic performance tuning method. Create performance models to help analysis and bottleneck identification, and use these kind of like as a guide that you go through the different settings, what you're tuning, so that you have a clear understanding of what you're looking at, and you have a clean way to do measurements and also validate that the tuning actually is effective. This will incrementally take you to the point that you learn how to tune and the brokers, bookkeepers, and zookeepers in a way that it meets your requirements and use case. Please contribute to Apache Pulsar. Like contributions are welcome also in this area, like for example to the documentation and feedback on the mailing list. GitHub discussions in Slack are also important contributions. Thank you.